Hey folks, I'm Jen Foxbot, and welcome to my episode on calculus. Woo! So I really think calculus is super interesting, and one of my professors told me, don't let the symbols push you around, you push the symbols around. And I really loved that because for a long time I was kind of intimidated by certain types of math. And when he said that, it was like, oh, math is just a language, look at that. And that really helped me understand what it is that we're using math for and what it actually means. So I wanted to share why I think calculus is super cool and what it actually does for us. Like, how does it actually apply to the real world? So for this episode, I'm going to focus on differential calculus or derivative calculus. I'll make another one on integral calculus. So yeah, here we go. Let's get started. So first of all, anytime we're dealing with mathematics, it helps to set up a coordinate system because that allows us to be super precise. So for calculus, let's do this. Boop. I'm going to set this horizontal axis as time, and we'll say seconds. Yay, units. And we'll set the vertical axis as position. And I'll call that X, and we'll use meters because, hooray, metric system, it's a lot easier. So let's say, for example, that I want to figure out how fast I walked away from my house. Say I was going to the train station or something like that. Boy, that really does sound like a textbook problem. If train A leaves the station at 2 o'clock, how fast is train B going? You're like, what? Anyway. So let's say I walk at a constant pace and I go this far. So that would look like this. I just draw a little line. And so let's assume it took me, 5 seconds to go 10 meters. So now we're getting into calculus. So what we can do is we can say, okay, let's find how fast my position changed over time. So I can do that by calculating the change in position. And we can use a little operator called delta, which is just a little triangle like so. So delta x over delta t. This might be a little familiar to you. So in this case, my delta x is 10 meters, and my delta t is 5 seconds. So that would give me 2 meters per second. So basically, by doing some rough calculus on this path, I can figure out how fast I was traveling. So based on that, 2 meters per second. That's pretty quick, right? Huzzah. Maybe I was walking fast like those walkers in the Olympics. Cool. That's great. But why is that so important for calculus? So this is kind of like a quick and dirty example of what you would do before you started taking derivatives. So to take a little bit more complicated example of why we would need calculus, so let's say instead of a constant rate, I'm kind of walking all over the place. I stop at some point and smell the roses, and then other points I'm like, oh, I'm late, no, I'm gonna miss my train. And so I speed up. So now all of a sudden, I don't have that nice straight line, and this sort of still works. You could say that my average pace from my house to 10 meters away, it's a close train station, was 2 meters per second. That's cool. But let's say I wanted to find how fast I was going at that point, or this point, or this point. So that's where you would need a function for this curve. And we use typically like f of x. In this case, it's going to be f of t because my function is going to depend on time. And so what calculus allows us to do is find how fast I was traveling at any given point along this curve. And how I would do that is just by taking the derivative of f of t. So let's see, where else can you see? So there's a few different ways to represent that. You might have seen d dt, so I would just do f of t. You might have also seen f prime of t. There's a few different ways to write this. I believe that's Newton's notation and that's Leibniz's notation, maybe? I might be getting that backwards. But anyway, these are just different ways to represent the exact same thing. So these two things are saying same thing. Basically what we're doing is we are finding how much our curve is changing over time. And that's super crucial because it allows us to do really cool things. Like say, for example, I turned my heater on in the winter and I wanted to figure out how long it would take my whole room to heat up. Well, I could find a function to represent that, and then I could take the derivative and be like, haha, it's going to take 10 minutes for my room to heat up. And I could actually calculate the temperature at every given point and how fast it would be changing, which is super cool. Alright, so I'll call it good for now. Please let me know if you have any questions. I will do another video on integral calculus. But yeah, thanks for watching and see you next time.